In this video, I'll be going over transformations of functions. So what this means is if we have a function, how do we move that function around in the xy plane? How do we reflect it, or how do we stretch or shrink? So in order to do any of these transformations, we must know what the most basic forms of various functions are. So this chart shows what we can call the parent functions. Sometimes these are called the toolkit functions. Basically, it's the simplest form of various functions. So for example, the identity function, y equals x, this is just something that is linear. Okay, so a linear function that is transformed could look something like this. So y equals 5x minus 2. So it's still a linear function, but the 5 and the negative 2 are transforming that function into something else. The squaring function, so this is just a quadratic. If we had something like this, 3x squared plus 5, that is going to move the parabola away from going through the origin and somewhere else in the xy plane. So that's the idea with these parent functions and how we can transform them. So what we need to be able to do is take something that looks like this and determine, well, what is that 3 doing to the graph, and what is the 5 doing to the graph? And so we need to identify what the parent function is and then describe what the transformations are. So there are a series of different types of transformations. We could have a horizontal shift. So for a horizontal shift, if we are given function y equals f of x, if we have y equals f of x minus c, that is a right shift. If we have y equals f of x plus c, that's a left shift. And that c is just telling us how many units, either to the left or to the right, we are moving. So an example of this, let's say I had y equals x squared. If I had y equals x minus 2 squared, that's going to be a shift right 2 units. If we had y equals x plus 2 squared, that's going to be a shift left 2 units. Moving on to a vertical shift. Again, if we have a function y equals f of x, if we have f of x plus d, that means we're moving up d units. If we have f of x minus d, we're moving down d units. So suppose we have y equals absolute value of x. Y is equal to absolute value of x plus 5 is going to be moving that absolute value function up 5 units. And then y equals absolute value of x minus 3 is going to be moving the function down 3 units. So if we compare kind of what's happening between the vertical shift and the horizontal shift, the signs are different, and so that's we need to take special care of that. So when we have a horizontal shift, when we are subtracting a value in here, our intuition might say we want to move left whatever that c value is. However, for a horizontal shift, it's the opposite of what our intuition would say. So if we're subtracting a value, we move to the right. If we're adding a value, we move to the left. This is the opposite of what happens for a vertical shift. If we're adding a value d, we're moving up. If we're subtracting a value d, we're moving down. So for a vertical shift, it's more in line with what our intuition would say. The next set of transformations are the reflections. So if we have y equals f of x, a negative inside the input is going to reflect about the y-axis, or a side-to-side reflection. If we put a negative in front of the function, that's going to reflect about the x-axis, or a reflection flipping the function upside down. So if we have a function, let's say y equals x cubed, if we said something like y is equal to negative x cubed, that's going to be a reflection about the y-axis. If we say y is equal to negative of x cubed, that's going to be a reflection about the x-axis. Next up is a vertical stretch or compress. So given y equals f of x, if we have a constant a times f of x, we say that that is a vertical stretch or compression by a factor of a. All right, and then we would say if a is greater than 1, this is a stretch. If a is between 0 and 1, this is a compression. All right, so as an example, suppose we have our function, let's do something we haven't done yet. How about square root of x? So y is equal to 2 square root of x. That's going to be in this case because a is greater than 1. So that would be a vertical stretch by a factor of 2. If y is equal to 1/3 times square root of x, that's going to be in this instance where a is between 0 and 1. So this would be a vertical compression by a factor of 1/3. The last transformation to discuss is a horizontal stretch or compression. So given y equals f of x, y equals f of b times x is a horizontal stretch or compression by a factor of b. So if b is greater than 1, this is going to be a horizontal compression. And if b is between 0 and 1, this is a horizontal stretch. Okay, so lastly, as an example, let's say we have the absolute function, or absolute value function. If y is equal to absolute value of 3x, that is going to be this instance. So it's going to be a horizontal compression by a factor of 3. If y is equal to 1/2 x, that's going to be in this instance because the b value would be between 0 and 1. This would be a horizontal stretch by a factor of 1/2. One thing that is kind of special or unique, or something we need, something we need to be careful about with a horizontal stretch or compression is if we have a function like this. F of x equals 4x plus 2 squared. Now, we need to be careful because this 4 right here, it looks like that is a horizontal stretch or compression. And there is a horizontal stretch or compression, but what we need to do first is factor out that 4. That's going to be left with 1/2. Okay, so we want to get a coefficient of 1 on this x here. Okay, so now there are a couple transformations that are happening. This 1/2, this plus 1/2, we would say is left 1/2 units. And then the 4 is going to be, we're up in this instance. So we'd say a horizontal compression by a factor of 4. Okay, so we need to be careful because this 2 right here becomes a 1/2 after we factor out the 4, and this really is moving this function left 1/2 units, not left 2 units. So it's vital that we factor out that 4 first. And this is going to become something vital when we are graphing trig functions, and we'll see that in a different section. And I want to summarize all of these transformations with one thing. So anytime we have anything that is horizontal, that is always happening inside or with the input of the function. So when we have a horizontal stretch or compression, this b value is acting on the input or the x of the function. Over here, and the horizontal reflection, or about the y-axis, is a negative inside the function. Similarly, a horizontal shift, we're adding or subtracting c on the inside of the function. Conversely, anything that happens outside of the function is a vertical shift. So here we're adding or subtracting d, that's a vertical shift. When we put a negative outside the function, that's a reflection about the x-axis, which is flipping it upside down, which is a vertical reflection, and then multiplying by a coefficient a outside of the function is a vertical stretch or compression. So this is one way that you can categorize each of these transformations. So let's look at a few functions and describe what their transformations are. So the first one, we have f of x is equal to 1 over x plus 2. So when we're doing these problems, the best thing to do is to identify what the parent function is. And this parent function is the rational function 1 over x. So the only thing that's happening here is we're adding 2. Because this is outside of the function, this is going to be a vertical shift up 2 units. And if we wanted to see what this graph looks like, well, let's think about the parent function. There's 1 over x. So if we wanted to shift this up 2 units, well, now we're going to have the asymptote at 2. So it's maybe not very clear to see, but that whole function gets shifted up 2 units. Next up, we have f of x equals negative of x plus 1 cubed plus 2. So the parent function here is going to be f of x is equal to x cubed. That graph is going to look like this. All right, so what are the transformations that are happening? Well, we have this 1, this negative symbol, and the 2. So how you want to think about this, or go about this, I should say, is start on the inside of the function and work your way out. So the 1, that's going to be left 1 unit. The negative symbol is going to be a reflection that's outside the function, so it's a vertical reflection, so it's a reflection across or about the x-axis. Let's try that again, axis. And then the 2 in the back is going to be up 2 units. So graphing this is going to be a little hard to see, but we're shifting the graph from going through the origin. We're shifting left 1 unit. We're going to reflect, so it would be a decreasing graph, and then it's going to go up 2. So the graph is going to look something like that. Okay. Now, my suggestion would be to graph the parent function and this new transformed function with technology, either on a graphing calculator or in Desmos, to get a more precise view of what these two graphs look like together. All right, for the next one we have f of x equals 2 times the cube root of 1 minus x plus 4. So the parent function here is f of x is equal to the cube root of x. And the cube root function is an increasing function. Looks something like that. It's not a very good graph. Let's try that again. So we have a few things going on here. We have the 2, we have the plus 4 on the back end, we have the minus x, and the 1 here. So let's just clean up how this function is written. I'm going to swap the negative x with the 1, write it like this, and then like we saw previously, it's a good idea for x to have a coefficient of positive 1. So let's rewrite this as, right now, the coefficient is negative 1. So I'm going to factor out a negative 1. I end up with x minus 1 plus 4. So now we can clearly see what the horizontal shift is and what the horizontal reflection is. So putting this all together, this right here is going to be a shift right 1 unit. This negative 1 in front is going to be a horizontal reflection. So reflect across the y-axis. The 2 is a vertical stretch by a factor, vertical stretch by a factor of 2. And then we're going to go up 4 units. All right, so that's it. So in order to graph this, it's going to be a little bit messy, but the best thing to do is to take the origin point, shift that to the right 1 unit, and then we're going to reflect that across the y-axis. So now reflecting across the y-axis brings it over here, and the graph would now be doing something like this. Okay, and then I'm going to vertically stretch that by a factor of 2. So what that means is, imagine this graph was like rubber, and I'm going to pull it up and down. So it's going to make the graph steeper. So it's going to be more something like this. I don't know if that's pronounced enough. Let's try that again. So it's not shifting up, but the curve is just going to be sharper. Okay, and then we're going to go up 4 units. So we're going to end up with something like that. And again, you don't have to be entirely precise. The idea with transformations and using them to graph is just to get an idea of what the graph is going to look like. For the fourth one, we have f of x equals absolute value of 1/3 x minus 2. So the parent function is the absolute value function, which that graph looks like this. Okay, so the transformations, we have a 1/3 and we have a negative 2. So again, start inside the function and work your way out. The 1/3 is a horizontal, it's either a stretch or a compression. Because it's between 0 and 1, it's going to be a stretch. So horizontal stretch by a factor of 1/3. And then the negative 2 says shift down 2 units. So because this is a stretch, this V shape is going to get wider, and then we're going to shift down 2 units. So it's going to be something like this. And there you go. And then let's look at these last 2 examples. The first one says, write the function for f of x equals x cubed that is shifted down 4 units left, stretched vertically by a factor of 3, reflected across the x-axis, down 2 units. Okay, so we're going to say left 4 units, so that's going to be x plus 4 cubed. Stretch vertically by a factor of 3, so that is a 3 as a coefficient. Reflect about the x-axis, so the x-axis is going to be a vertical reflection, so that's going to be a negative in front, and then we're going to shift down 2 units. So that's what we would get. That's what we'd get for that one. And then for the last one, starting with x square root of x, we're going 3 units right, about the x-axis and 1 unit up. So this is going to be f of x 3 units right, so we're going to say minus 3 inside the function. Reflected about the x-axis, so that's a vertical reflection, shifted up 1 unit. Now suppose this said shift about the y-axis. So this would be f of x is equal to, okay, so we're going to say square root. Let's start with 3 units to the right. But now since we're reflecting about the y-axis, we need to make this expression negative, and then we're going to shift up 1 unit. Now, if we think about this, if I was to distribute that negative through, we'd end up with negative x plus 3. Now that doesn't look like we're shifting any longer to the right 3 units. So what we actually need to do is make this a positive 3. So we end up with that. So that's what we would have to represent this simple change of reflecting about the y-axis. So graphically what we'd have here is, so first we have this as the radical function. Okay, so we're shifting to the right 3 units. So we're going to move this over to 3. And because this becomes a negative 3, that is corresponding to what we have. And then we're going to reflect about the y-axis. That's what this negative is doing. So reflecting over here, and then we're going to shift up 1 unit. So that would be the correct graph to be represented by this new function. All right, so that's it for this video. Hopefully you better understand how transformations of functions work.